Hi everyone. Today I'm going to present to you a recent project I've been working on together with my colleagues at Assent in Forschungszentrum Juelich, and you can see the names under the title. The title is Summation Compression for Very Low Rank Adaptation, and the project is about parameter efficient fine-tuning. So let's see this in detail. So we have a pre-trained model and a target downstream task, and we want to fine-tune the model to the task efficiently, where efficiently is either memory efficiency or computational efficiency, but ideally it's both, and yeah, while maximizing the performance. We do so through the means of parameter efficient fine-tuning, or PEFT in short, which targets to fine-tune a very small number of parameters as a proxy for efficiency. And so these methods can be applied to many tasks, and we do so. We apply to image classification, monocular depth estimation, image generation with diffusion models, and mathematical reasoning with LLMs. Yeah, so again, what is parameter efficient fine-tuning? It's like either finding a subset of the parameters in a model to fine-tune such that it's faster and while achieving possibly the same performance as fine-tuning the full model, or introducing new parameters such that the count is small enough that allows for fast fine-tuning. So here you can see the baseline we considered. I'm not going to go through all of them, but what's important, and it's not even specified, it's that in this work we consider the lowest possible amount of parameters per method, and when it's possible to go even beyond, we still stay in a comparable way. So we stay comparable to d parameters per layer. Yeah, so let's see, as a reference we will see LoRa, low rank adaptation. So you have a pre-trained matrix, which is the W0 matrix, is blue because it's frozen. It's not specified, but yeah. Blue in this case means frozen, and yellow means fine-tunable. So this, so LoRa introduces a low-rank representation of the original pre-trained matrix, such that the parameter count is smaller, and it's fine-tuning those two A-B matrices results in faster fine-tuning and possibly same performance as fine-tuning the full matrix. So in this context, I like to call A and B compression and decompression matrices, and we go beyond this, and we consider compression vector. And we use the sum as compression vector. So we introduce this one LoRa or iLoRa, which uses basically a single vector as compression, and it's just a vector of ones, and then a single vector as decompression, which is a vector of d parameters. As a context, d parameters means it's the same as a bias vector. So basically, it's the same as the first method that only fine-tunes biases. But the difference is that in this case we input the data through to the module. So the difference with LoRa is that in this case we have the outer product between these two vectors. One is the one vector, the sum, and the other one is the only vector of d parameters. So why would this sum work? So there are other methods doing this. Like in this case it's the one before us, Mora. But ideally, it's basically, the intuition is that, so nonlinearities like ReLUs move features towards the positive orthant by suppressing negative values. So using a vector of ones strongly correlates. And here on the left, you can see this image. We test this empirically. So on top is classification, on bottom is monocular depth estimation. And this shows the absolute cosine similarity to the principal components of the full update. And the similarity is computed between summation, so the sum vector, random vector, or learned vector of LoRa with rank 1 to the full update, to the principal component of the full update. And the first three columns represent layers that are before nonlinearities, and the last column is multilayer perceptron right after the ReLUs or whatever activation function is used in the model. Starting from the right column, basically we see that basically there is a high similarity between using the vector of 1, so the sum, and the full update. And in the other cases, so for the other 3 columns, the similarity is low for all of the cases. So in general, we conclude that using the sum is efficient in terms of both memory and efficiency, and and computation. So let's see the performance. Also here is, we're not going to go to all the tasks that we computed, but so in this case it's monograph depth estimation. So in monograph depth estimation, the goal is to predict, estimate the depth given a single image as input. And in this context, we do a transfer from Kitty to NYU, which is outdoor scenes to indoor scenes. And we fine-tune a depth anything model. And the plot on the left can be interpreted as, so y-axis is a root mean square error, x-axis is time, and then bubble size is parameter count, and the bar plot on top is GPU memory consumption. So ideally the best case is bottom left is the best, and smallest bubble is also the best, and shortest bar is also the best. So ideally you would have all of the 4, so bottom left and shortest bubble and smallest bubble and shortest bar. And as you can see in the plot, the yellow bubble, which is our method, in this particular case achieves a very good trade-off between memory efficiency, parameter efficiency, speed, and performance. But yeah, let's move to another task. In this case, it's not computer vision anymore, it's text. So it's mathematical reasoning task. We fine-tune a Llama 2 model, 7 billion parameters, from pre-trained to MetaMath, a mathematical reasoning dataset. And yeah, so we already noticed that one of the methods runs out of memory, so Dora. But still, so in this plot, it's still visible that our method still has a good trade-off between performance, time, and memory and parameters. But there is one method that outperforms it in terms of performance, at least, and it's LoRa. So yeah, LoRa is, in this case, better. However, it uses more memory, as you can see, the brown bubble and the brown bar, and almost double the amount of parameters. So the question here was, what happens if we go to bigger models? So 7 billion is not big for LLMs. So we do so. So this is the same task. So it's the same task as before, but we just doubled the amount of parameters. So it's 13 billion. We fine-tune from 13 billion to MetaMath again, and you can see that like most of the methods run out of memory, including LoRa. And yeah, we can of course still compute these methods, but we need to target a subset of parameters. And so in this case, I show this in the light blue bubble. This LoRa QKV means it's only applied to attention layers, so QKV. And yeah, the parameter count is smaller because it's a subset, but it still uses the same amount of memory as we do. So in practice, the advantage here for our method is that we use the same memory as LoRa applied to a subset, but we achieve a little bit better performance. So in terms of performance, it's better while using on-par GPU. Of course, it takes a little bit more time, so it's like a trade-off, depends on what's the task, what's the goal. So in conclusion, yeah, we introduce iLoRa, so a path method that only uses d parameters per layer, leveraging the sum as fixed compression. We evaluate this on multiple tasks. We show good performance in terms of good trade-offs in terms of memory, speed, and performance. And yeah, lastly, we show that since it's memory efficient, we can better distribute trainable parameters across larger models. So instead of only targeting a subset of layers, you can target more layers, and this allows to improve the performance. This will be the last slide. I would like to thank you for your attention and thank my collaborators.
For this here interesting presentation. Do we have questions? Yes, I see someone coming up.
Thanks a lot for the talk. It's very interesting. I was wondering, which GPUs did you test it on?
It's A100s.
Okay, so you didn't test on others, I mean, which have more memory?
No, we use on so the supercomputing in facilities in Juelich. So it's A100s, 40 gigabyte.
Yeah, no, I understand. I was just wondering whether you could see any differences in if you say go to H100 or H200.
No, we didn't test that, no.
Okay,
Yeah.
thank you.
Then we have one more question up front here.
Yeah, thanks for the nice talk. I'm wondering, in LoRa, like you can adjust the length to adjust the number of trainable parameters.
Yeah.
Is it also possible for your method?
No, here it's like fixed. So yeah, the context of this work is like we want to go to the smallest possible. Mm-hmm. So yeah, this is very limited to the very low rank regime. So it's.
And can you also describe the difference between your method and LoRa with rank 1?
Yeah, LoRa with rank 1 is yeah, it's there. It's using double number of parameters basically. Mm-hmm. So the weights in the compression vectors are still learned. Mm-hmm. So this is basically an approximation. Using the sum basically doesn't require to use to learn parameter in the compression.
Okay, I see. Thank you.
I have one more question. You did fine-tuning on a single GPU?
No, it's multiple GPUs. So in the case of Llama 2 13 billion is, I think, 64 GPUs.
Okay,
yeah.
Then it might be a bit of a nasty question, but you mentioned that you can reduce memory, but isn't that sort of, we've heard a lot about efficiency and computational efficiency as well. Isn't it wasteful to, let's say, have multiple GPUs that are then just using 40% of their memory, and wouldn't it make more sense to make them as full as possible and then use less GPUs?
Yeah, definitely, yeah. So when possible, it's better to have, so use the GPU fully, mm-hmm. and yeah, have reduced the number, yeah.
Okay, and did you, because I mean you showed memory.
So I think in this case it's almost fully used.
Yes, okay.
All of them, like 64 GPUs, almost fully used, yeah.
Okay, and did you have a look also at actual throughput in terms of performance?
Sorry, actual?
Throughput. So how many computations the GPU actually does?
I didn't have a look at that, no.
Okay. Ben, thank you.
Thanks.
And we move on to our next speaker.